This morning's session is a discussion led by Antonio Antunes from Porto about conformal field theories near the edge.
All right, thanks a lot, Sylvain, for the introduction. And I'd like to thank all the organizers for giving me the opportunity to speak at this wonderful conference. And Sylvain said, I'm going to be talking about conformal field theories near an edge. And I understand that by now it might not be clear what an edge is, but hold on just for a second. First, I'll just tell you what I'm going to do in this discussion, and then other people can intervene, of course. I just want to go over an old paper by Cardy called Critical Behavior at an Edge, a paper from the 80s, and then over a paper I wrote recently called Conformal Bootstrap Near the Edge that appeared on the arXiv a couple of months ago. So what is the edge? What am I talking about here? So I'm going to be studying conformal field theories that are constrained by two boundaries, so two infinite boundaries. So Mikola discussed boundary conformal field theories, and okay, we can introduce one boundary, say at the coordinate xd minus 1 equal to 0. And what we're going to do is introduce a second boundary, a second infinite plane, that intersects the first one with an angle theta. And since these two infinite boundaries intersect, there is a region, a submanifold of codimension 2, which is what I call the edge. And of course, this edge is infinite, and there's translational symmetry along this d minus 2-dimensional space. And I'm going to be using this x vector for the coordinates along this transverse infinite dimensional space. So, okay, we have this geometry. We have an infinite wedge, if you want, a cheese wedge. But now you might wonder, why am I studying this crazy geometry? Is there any good reason to think about this? And the first motivation is experimental, if you like. So real critical systems are bounded. They have boundaries. And of course, boundary CFT is very important. That's one of the reasons. And real systems are not just bounded on one side. They are bounded in more than one side. And therefore, real systems have edges. So that's one natural reason to study criticality in this scenario. Another reason is because when we have edges, as I said before, we have this angle theta, and this is a parameter that we can play with. And in quantum field theory, it's interesting to study how our observables depend on parameters. Usually we don't really have control over it when these parameters are, say, couplings, for example. We can only do perturbation theory and so on. So it's hard to understand how things depend on parameters. But this is one case where we actually have full control over the parameter. It's something that we impose on the system, like we are experimentalists, and we can just play around with it as we please. And furthermore, this is also interesting in the CFT point of view, because we like to think of CFTs as things that are very rigid. For example, the 3D Ising model lives inside a very tiny island. We cannot deform it and stay inside a CFT. But this gives a way to introduce parameters into CFTs, continuous parameters. So that's another motivation to study this. And of course, what are we actually going to study? What are the observables? The natural observables are critical exponents that we can measure, say, from two-point correlation functions of local operators. And of course, since we have all these two boundaries and we have this edge, we can imagine that there are many different critical exponents associated to letting the points go close to one boundary or close to one edge and so on. So that's the basic premise. Let me just say one word on notation. We have this d-dimensional bulk, this wedge that I was mentioning, and I'm going to be using a color scheme that is a generalization of Mikola's scheme from this week, which was blue for the bulk and red for the boundary. We have two boundaries, that's important. And then I'll introduce the color green for edge observables. So hopefully this will help guide the eye because we have many different types of operators. So, okay. With this in mind, I'll start by reviewing this short but very nice paper by Cardy from 1983, in which he just studied a Landau-Ginzburg ON model in the geometry, this wedge geometry that I just described. So Cardy wrote down the free energy. Everyone knows this ON model. We just have this ON symmetric quartic interaction. And to To formalize the boundaries, what one does, and this was also done in Mikola's talk, we introduce this quadratic term that is defined over the boundary with this parameter C. And we saw in Mikola's talk the case where C is negative, and this is related to the extraordinary transition, but we'll be focusing in the case of C positive, which is the so-called ordinary transition, where the bulk and the boundary are there at the same time, and basically means that they have the same critical temperature. So having C positive effectively means that C becomes very large at long distances, and C large suppresses the value of phi at the boundary. And what this means is just a formal way of saying that we have a Dirichlet boundary condition in terms of the free field. So this ordinary transition in the free field language is essentially the statement that we have Dirichlet boundary condition at the two boundaries. So this is going to be the setup for Cardy's calculation. We have an ON model with two boundaries with a Dirichlet boundary condition. Okay, so let's start computing. And the first step, of course, is to do mean field theory, where we just turn off the Quarty coupling and try to compute the two-point function of two operators inserted inside the wedge. As I mentioned, we have translational symmetry along the d-2 edge directions. And this means that we can just perform a transverse Fourier transform. And I introduced this transverse momentum K vector. And what remains is this small g propagator that depends on the remaining coordinates xd-1 and xd. But because of the symmetry of the system, this cylindrical wedge, it's convenient to actually work in polar coordinates. So in this xd-1 plane, we'll just be taking polar coordinates r and phi. And in red, I'm just showing these boundaries that make an angle theta. Okay, so now it's a straightforward exercise to solve Green's equations with these specific Dirichlet boundary conditions. It's straightforward, but the answer is actually quite complicated. Here is the answer that Cardy derived. We have an infinite sum over modes, which are the sine functions of the angle, and it's evident that they satisfy the Dirichlet boundary conditions at phi equals 0 and phi equals theta. And this works mode by mode, actually. But then we see that the position dependence is actually quite tricky. We even have an integral representation. So, okay, we have this complicated propagator, but how can we study critical exponents? Okay, we should, of course, make the mass go to 0, take the correlation length to infinity, and then study the correlation functions at long distances. Because at long distances, we will find power loss, and we will have the usual eta critical exponents for the correlation functions. But this is actually very rich, because since we have this color scheme of green, red, and blue, we can imagine that we can send points apart in many different ways, and we will find possibly different etas. And that's why I have these open slots here. There I'll have different types of etas. So one interesting limit is just the limit where the 2 points are in this xd-1 xd plane. And we just keep 1 point near the edge and send 1 point very far away deep into the bulk. And this is dominated by the n=1 mode in this summation that I showed you before. And if you do this analysis carefully, what you find is that the power law is, there is an anomalous dimension, there is this critical exponent eta, and it's given by pi over theta. So this is the first observation, is that we are in a free Gaussian field, but there is an irrational, generically irrational exponent. This is not too shocking because we introduced this parameter theta, so we expect these things to depend on theta. But okay, this is like the first main observation. Our bulk edge exponent is given by pi over theta in the Gaussian theory. We can consider a different limit. Take 2 points near the edge and shoot them far apart in the transverse directions. This is sort of an edge-edge type of limit. And here we find a different critical exponent that I called eta edge-edge. And it's just given by twice the bulk edge critical exponent. This is not too shocking. It's very similar to what happens in BCFT and so on, but it will be made pristinely clear in the CFT language that I will introduce bit later. And let me just finish this tiny section by saying that I'm just looking at the eta critical exponents, but one might be interested in the magnetism part. And Cardy also derived the edge magnetization and the edge susceptibility exponents, but I'll not talk about this. So I'll just be focusing really on the correlation eta exponent. Any questions so far?
Okay, I have a question. So
Yep.
the correlator that Cardy found, this integral expression and the sum and stuff,
Yes.
he was able to find this on a closed form, right?
You can do the integral in a closed form, but the position dependence will become a bit more complicated. Mm-hmm. And you cannot do the infinite sum. You will always have this infinite number of modes, and the physical interpretation of this number of modes will become more or less clear in a second. It has to do with this integer n. You cannot get rid of this infinite sum physically.
I see, I see. Okay.
And you can imagine doing it, but it has a nice interpretation, yeah. Sorry.
Right, right. And when taking this asymptotic limits, you have like this bulk edge correlator and so on. Do you find any divergence as you approach the edge?
I mean, you have this...
like something like
one or power law behavior.
Mm-hmm.
You just find this power law behavior. I mean, okay. If you take it strictly, yeah.
No, I mean, this is okay. I see. But this is so there one term, and this is the term you have up here.
That's right. This is you just mean field theory. Yeah.
Yeah. Okay. I see. Thanks.
Thank you. Thank you. Okay, so let's move on to the one loop calculation. So far we did mean field theory, and now let's go to the epsilon expansion to the first order. And we can compute the 2-point function, and we only need to write down one loop Feynman diagram, which is this one. It's the tadpole. It looks very simple, but it's actually a very technical calculation. It's probably the hardest tadpole calculation I've seen. And the reason why it's hard is that, of course, these propagators are devilish. As we saw before, they are quite complicated. And since the system actually breaks quite a few symmetries, we have to perform integrals on several different variables. So, I mean, it gets pretty tough. And the way Cardy handles this is by actually looking at very specific limits of the integral. So the first thing he does is immediately take this bulk edge limit, just take r to 0. And this allows him to focus on a specific piece of one of the propagators. And then he actually does only part of the integration, essentially by keeping track of what parts of the integral could generate logarithms. And that's just because we know that these logarithms will be associated to these corrections of the OP coefficient. And here you will get these logarithmic divergences that Alexander was worried about at this one loop calculation. But one just tries to keep track of the logarithmic dependence. And Cardy was able to do this, and his observation is that this logarithmic behavior comes only when the bulk integration, comes only when the bulk integration approaches the edge. So these divergences are really an edge effect. It's an intrinsically intrinsically edge physics. So, okay, we can go.
No, but wait, sorry. Sorry. I mean, these are going to zero. I mean, shouldn't you find also divergences when you approach one of the boundaries?
I mean, you could also, but Cardy just wanted to find the simplest way to get the critical exponent. Mm-hmm. And the way he did this was to focus from the beginning in the bulk edge limit, because otherwise the integral is just too hard. Mm-hmm. So by doing this r going to 0 limit, you immediately take only the leading mode in one of the propagators, because otherwise you have 3 infinite sums. Okay. So this is basically the fastest path to getting the critical exponent.
Right, I see. Thanks.
Thank you. So, okay, we do Cardy's exercise. I won't show you the details of the integral, but the answer is this. Here's the order epsilon result for the anomalous dimension. It has a quite non-trivial dependence in theta. And for the experts in BCFT, this bulk edge anomalous dimension actually reproduces the bulk boundary anomalous dimension when you take theta going to pi. When theta goes to pi, this just becomes 1, and people will recognize this factor as the anomalous dimension in usual BCFT. So as I was pointing out, this is a one parameter deformation of a conformal field theory. And let me finish discussing Cardy's paper by pointing out that he actually did something more rigorous than this analysis I discussed. He really did an RG formulation of this by actually doing renormalization of the edge. And how did he do it in practice? Of course, the main idea is that we associate the exponents to the UV divergences. That's renormalization. And the way to do it is to define an edge mode. So an object that lives strictly on the edge by taking the bulk field and its expansion and taking a limit as you approach the edge with a specific prescription. This prescription comes from looking at the mode expansion of the field. And when you define this object, you can of course couple it to your Hamiltonian by turning on a magnetic field along the d-2 dimensional submanifold. So when you turn on this magnetic field, you can of course have an associated edge renormalization constant, and you can write down an RG equation for this. And this allows you to compute all bulk and edge correlation functions using the RG equation. So, and in the end of his paper, Cardy basically reproduces this one loop result by using the RG equation. So that's what Cardy did. And if there are no questions about this, I'll move on to what I did in this recent paper, which is to try to formulate the physics of this wedge system in terms of conformal symmetry and conformal bootstrap. Are there any questions on this Cardy work? Okay, so I'll move on to the bootstrap then. So the first step in the bootstrap, of course, is to try to take advantage of the conformal symmetry. And let's go into steps. Let's restrict our geometry step by step. So we imagine that we have this d-dimensional bulk CFT, it's homogeneous, and it has the conformal group symmetry, SOD plus 1, 1. Then we introduce one boundary. And by introducing a boundary, we are breaking translations in the normal direction to the boundary, of course. And we are also breaking a special conformal transformation. And we are breaking rotations that move away the normal vector of the boundary. And this analysis was done long ago by Cardy as well. And it turns out, and summarized also nicely in this McCafferty and Osborne paper that has been mentioned this week, and the symmetry that remains is SOD, 1, which is of course the conformal symmetry in d-1 dimensions, which we interpret as the conformal symmetry that acts on a boundary. But now we introduce the second boundary that intersects with the first one. And the second boundary, of course, will also break a translation and a special conformal transformation, and it will break some rotations as well. And what remains, if you do this analysis carefully, is an SOD-1, 1 symmetry, which is just the conformal symmetry of a d-2 dimensional space. And of course, we interpret this as the conformal symmetry of the edge. So for people who are experts on defects, this is very different from a defect, because if we had a codimension 2 defect, we have rotation symmetry around it. But here we just explicitly broke this rotation symmetry. So the physics is quite different. And let me...
So I mean, yeah, now that you mentioned defects, this looks very similar to a monodromy defect, right? Like, I guess if you identify the two boundaries, that would be exactly the same thing as a monodromy defect.
That's a good point. That's a great point. So this is like the open string version of a monodromy defect, if you want, in the sense that we have a boundary. Yeah, that's a good observation. Yeah. But it's different, right? Because here we have the boundaries, and the boundaries lead to singularity, so the physics will be totally different. You agree?
Yeah. It's just that it's similar to defects. That's the only thing I wanted to say.
I agree. Thanks for the comment. So let me point out that this relation between SOD, 1 and SOD-1, 1 allows us to make this cute observation that the boundary theories are actually BCFTs themselves. So this is a two-tier BCFT system. And what does this mean? It means that the boundary theory has a boundary. And of course, the boundary of the boundary is the edge. So this is going to play a crucial role because we're going to be able to compute observables using this mechanism, that we have a two-tier boundary CFT relation. Okay, So we discussed the conformal symmetries. Let's look at the observables. I'm going to be using this notation with hats. So this is standard to use bulk operators without hats and boundary operators with a hat. And I'll introduce a second hat for the edge operators. So the first interesting thing we can study is the bulk one-point function. This is interesting, and I'll tell you why. Let's try to fix it from conformal symmetry. So first, we can write down the scaling part, just from scaling, which is just the power law with the right dimension. But then we have one invariant quantity, one cross ratio, which I call eta, which is just xd minus 1 over xd. And of course, this is no more than the tangent of the angle in this xd minus 1 xd plane. So if we have the operator making an angle phi here, this is a cross ratio, because conformal transformations cannot shift the angle in this plane. We only have conformal transformations along the edge. So this is already a non-trivial correlation function. It depends on a cross ratio. And furthermore, it depends on the parameter theta that we were discussing about. So immediately, this is a non-trivial object. And I would like to make this comment related to Alessandro Galvani's talk in the first week about this Yamabe equation, which is in principle a way to try to fix the one-point function of, say, for example, the 3D Ising model in certain geometries that are bounded. They did it in a slab. We might wonder if this Yamabe equation on a wedge would immediately tell us what this function is. From kinematics, it's not at all obvious. It's a function of a cross ratio, so we don't know what it is in principle. So it would be nice to see what can be done with that, and also to test it. Another observable that we're going to look at, which is of course related to the ones we also saw in Cardy's paper, is the bulk edge two-point function, but now we can formalize it in terms of a bulk operator and an edge operator inserted at the edge. So here, conformal symmetry fixes this form for the scaling part. We already have to look at this edge scaling dimension, which is a new object. We didn't have it before. We have these new edge operators. And of course, there is still a function of the cross ratio, which is basically the same cross ratio. It's just the angle. And we also have our parameter theta. So these are the interesting observables, the ones that depend on cross ratios. But we also have some new observables that are somewhat simpler since they are fixed by symmetry, but they are associated to new CFT data. And these are the boundary one-point functions. So in a boundary CFT, the one-point function of a boundary operator vanishes, but it's not anymore true because once you have a boundary operator, the boundary operator lives on a BCFT and the edge is there. So therefore, the one-point function can depend on the distance to the edge. And we have this coefficient, which is the boundary one-point function coefficient. And this is a new object. So I'm using this A hat to emphasize that it's something intrinsic of the boundary OPE, of the boundary operators that you couldn't see normally. We can also interpret this coefficient as a boundary to edge expansion coefficient, where the edge operator is just the identity. And this interpretation, of course, generalizes nicely to the case of a boundary edge two-point function, where we have a boundary operator and an edge operator. And this is, of course, fixed by symmetry. But now the associated CFT data is this boundary to edge OP coefficient between two generically non-trivial operators. Okay, so we've established all the kinematics. We established the CFT data that exists. But now we need to find a way to compute these non-trivial observables that depend on cross ratios. And the bootstrap way to do it is to find down a conformal block expansion. And what I'm going to tell you now is what type of OPE can we use to derive a conformal block expansion for this system. And we're going to take advantage of the usual boundary OPE. So the idea here is that we take a bulk operator, and this was discussed in Mikola's talk, for example, and we expand it in terms of a basis of boundary operators. And we can do this, even though we have an edge, for the same reason that in usual BCFT, we can still do the bulk OPE. We just need to be far away from the boundary, and the bulk OPE is fine. So this is basically the same thing. As long as we stay away from the other boundary, we can expand in a basis of operators of this first boundary. And this is the boundary OPE. we write a bulk operator in terms of power series expansion, in terms of the distance to the boundary. In this case, I chose xd minus 1. This is the vertical boundary. And of course, we have our boundary operators, which I'm labeling here by some integer n. And to take account into the contribution of descendants, we have this differential operator that acts on it. So now let's use this inside a correlation function and try to derive a block expansion. So for the block expansion of the bulk 1-point function, with respect to this first boundary at xd minus 1 equal to 0, we find the following. So we just need to take an expectation value inside this OPE. And as I mentioned before, this is just the boundary 1-point function that depends on the distance to the edge. And this effectively has already produced for us a block expansion in the sense that we have some CFT data here. This CFT data is already known just from the usual BCFT. And we have some new data that appears in this edge theory. And the rest, the position dependence, is completely captured by these kinematic objects. And in particular, since these differential operators were derived by McCavity and Osborne, we can try to do this explicitly. We can get a block expansion. Here it is. We write the dimensional prefactor and then a sum over some expansion coefficients and a conformal block. And I'm calling this conformal block the wall channel conformal block just because I'm using the vertical boundary to expand. These expansion coefficients are no more than the product of the bulk to boundary OP coefficient and the boundary 1-point function. I'm using these colors to emphasize that this is this edge data that is new. And as I was saying before, since we have access to this explicit operator that captures descendants, we can actually resum and write down an explicit formula for the conformal blocks. I derived this in my paper. And it's actually very similar to the BCFT blocks. I mean, the experts will certainly recognize the similarity. So, okay, we have the blocks. So we achieved one step in the Bootstrap program. And the next step in the Bootstrap program is, of course, to impose a crossing equation that allows us to solve for the CFT data. So we've reduced correlation functions to knowing CFT data, but now we need to solve for the CFT data. And for that, we write down a Bootstrap equation. And it's very easy to see what that Bootstrap equation is going to be. The idea is that so far we were expanding with respect to the boundary at xd minus 1 equal to 0, which I call the wall channel. But we might have, could have just as well have expanded on the other boundary, which I am going to call the ramp channel because, okay, in these conventions that I picked, this looks like a ramp. And it's very easy to cross to this channel. We just have to shift our axis, rotate by theta, or by pi over 2, theta minus pi over 2. And then we just have these Cartesian coordinates that allow us to expand with respect to the other boundary. So all we need to do is replace xd minus 1 by this other set of coordinates. And effectively, in terms of the cross ratio, what this crossing relation is doing is basically sending phi to theta minus phi, which is obvious, right? Instead of approaching this boundary, we are approaching this boundary. And okay, we can write down this crossing equation, which is just setting the wall channel equal to the ramp channel. I drew it here diagrammatically. And this equation, of course, can be written in terms of the correlators of the function of the cross ratio. Is a function of phi should be equal to a function of theta minus phi. Generically, this could be a different function. And the reason is that the physics in this boundary could be different from the physics in this boundary. And this is easiest to see in terms of the conformal block expansion. So we write down our conformal block expansion in the direct channel. We have a sum over blocks. We have a ratio of the prefactors, and then we have a sum over the blocks on the other channel. And clearly, this sum could be over a completely different spectrum, a completely different boundary conformal boundary condition, if you want. And that's why generically we can have different functions. But of course, you might expect that there exists some class of solutions where the same boundary condition happens on both boundaries. And then you will have the same coefficients and you will have the same function. Any questions about this crossing relation? Okay, so I'll try to find some solutions to crossing and try to connect to Cardy's work. So the first step is to try to solve crossing for the 1-point function, which is what we've derived here. And the simplest example I can think of is just computing a 1-point function where there's actually just a boundary at xt minus 1 equal to 0. And the other boundary is just a trivial boundary. There's nothing there. So we can take this 1-point function. Of course, it only contains the identity block in this direct channel. It's just a normal boundary CFT 1-point function. But we can expand it in the ramp channel. And if you just work this out using the explicit expressions for the blocks, you find that in the ramp channel, there is an infinite tower of operators that I call delta hat n with dimensions delta plus n. And this is, of course, very similar to what happens in the 4-point function bootstrap, where we have these double traces, these double twist operators of dimension to delta plus L. And this is also a reason to emphasize that this is not just a trivial academic exercise. This is a useful thing to do, this simple case, because it amounts to inverting the identity block, which is something that can be useful. This identity block will dominate the physics in certain OP limits, if the theory has this identity contribution. So, okay, we basically did the inversion of the identity. Another interesting example, and that is quite studied in the BCFT case, is a free bulk field, which is basically just a scalar operator of dimension d minus 2 over 2. And we know that this saturates the unitarity bound. This imposes that there are a bunch of null descendants. This is just like the free Klein-Gordon equation of motion, essentially. And what happens in this case is a huge simplification, because we can solve the crossing with just a finite number of blocks on both sides. And this also happens in the BCFT bootstrap. And these two blocks are related to these boundary operators phi hat, which have the same dimension as the bulk field, and this boundary operator derivative of phi hat, which has boundary bulk dimension plus 1, which we usually interpret in terms of classical boundary conditions, Neumann and Dirichlet. In particular, this block is thought as the Neumann block, and this is thought of as the Dirichlet block. And it turns out that a generic solution to this free bulk field crossing equation is composed of an arbitrary sum of these two blocks. And what is not arbitrary and what is fixed by crossing is the OPE coefficients in the cross channel. We can find this by using the explicit expressions for the blocks, and we find these relations between the coefficients. They're not very important. What is important is to note that if we want to connect to Cardy's boundary condition, where we did perturbation theory, so this Dirichlet boundary condition, we should set the Neumann block to 0 on both channels. And to make this equal to 0, it turns out that we must make the correlator vanish for generic theta. This is not shocking, because with Dirichlet boundary conditions, the expectation value of phi is 0, say for a single boundary. However, I note that there are some special angles, theta d, that depend on dimension d, where you can formally have a non-vanishing 1-point function. So I think it's a cute observation. But now we really want to connect to Cardy's results. And for that, we need to study a 2-point function. And the simplest one we can attack is the bulk edge 2-point function that I was discussing before. So this is actually a very mild generalization of the bulk 1-point function. We just introduce this edge operator here with 2 hats. And what happens now is that when we use the boundary OPE, we are left with boundary operator, but now we have reduced the calculation to a boundary to edge 2-point function. And these are slightly more complicated, but they are still fixed by symmetry. And if you turn the crank and you do the calculation, what you get, okay, you write our dimensional prefactor. Now we have this interesting edge dimension, which is an interesting observable. We have our new expansion coefficients, which depend on the boundary to edge operator expansion coefficients. This is new data that was not showing up before. And we have a more complicated conformal block that can now depend on the dimension of the edge field. And in my paper, I also derived the expression for the conformal block. And you can see that it's essentially just introduces a shift that depends on the edge dimension. And of course, we can write down the crossing equation by requiring the ramp channel and the wall channel to match. So that's it. We are now in a situation to try to bootstrap Cardy's result for the bulk edge 2-point function. So let's do it. Let's try to solve crossing for the bulk edge 2-point function. We can, of course, do the trivial boundary case, but I'm going to skip that. And I'm just going to talk about the free bulk field. And it turns out that you can once again solve the crossing equation with finitely many blocks on both channels, this Dirichlet and Neumann block. And the answer is a minor generalization of what we found before, with a very interesting detail, is that we have a shift by the dimension of the edge operator. And now, if we want to consider the specific solution that Cardy studied, which is the Dirichlet solution, of course, this is more general. It's a general linear combination of Dirichlet and Neumann. We can actually impose this condition. As I said before, we set the Neumann blocks to 0 on both channels. And now we can consistently set this equation to 0 for generic theta. Why? Because we can very carefully choose the dimension of the edge operators and make the sign vanish. And it turns out that the choice of edge dimension that makes this work is precisely what Cardy found, this d over 2 minus 1 plus n pi over theta. This n corresponds to these different modes that we were finding in this infinite sum. And of course, the leading one is just n equals 1. It's the most relevant edge operator. So we are able to reproduce Cardy's result, the free field result, just by taking a finite number of conformal blocks, which dramatically simplify because it's free fields. And it follows just from crossing that the dimension of the edge operators must be of this type. And let me mention just one last thing, which is that in this case, we can write down the 2-point function, bulk edge 2-point function. It's extremely simple. The angular dependence is just this sign that is very natural, as we saw from the free field point of view, from this mode expansion that Cardy derived. And another thing that we observed is that the dimension of the field being free doesn't really play much of a role in crossing symmetry. So in particular, we could have written down a solution for arbitrary delta. And this is still crossing symmetric, and this is a generalized free field solution. So this gives another solution to the bootstrap equations on a wedge. And this is slightly more interesting just because, okay, the correlator itself is simple, but the block expansion is already non-trivial because we will have infinitely many operators on both sides in both channels. So this is another solution to the wedge. So, all right, let me sum up and just mention some future directions, and then I'll ask if other people want to intervene. So the main goal of all this was just to point out that critical systems near an edge have interesting observables. They are very rich. We can play around with parameters. So there's plenty of things to explore. And it should be, these things have not been explored much. And I'm just pointing out that this is another set of problems that can be explored, particularly in the language of the conformal bootstrap, because we have access to conformal invariance and we can write down bootstrap equations. That's just my message. This is a new type of setup where we can do conformal bootstrap. And it might be interesting for several phenomenological applications. And in particular, the applications I have in mind, first of all, is the order epsilon bootstrap, which you might complain I didn't do. And experts on BCFT will tell me that, okay, in the boundary bootstrap case, we can do the order epsilon with a finite number of blocks. Why didn't you do this? And the answer is that in this wedge problem, we already need infinitely many conformal blocks at order epsilon. So this is a problem that needs to be tackled. I think the technology is available in work done by Agnese Bisi, Tobias Hansen, Alexander Soderberg, Parijat Day. I think the technology that these people developed can be used to try to reproduce Cardy's epsilon result and a huge tower of new data. So that's one goal I think is clear. And another goal is just to do the numerical bootstrap directly for the 3D easing model on the wedge. And I presume this subject has lost a bit of popularity, but in the 80s and 90s, people were doing some Monte Carlo work on this. So there is probably data to compare to. And I think that it would be nice to tackle it, at least using the Gliozzi method, because the operator coefficients, expansion coefficients we were writing down were clearly not positive. They were not squares of anything. And in particular, they are not positive on both channels. So it's a very non-positive bootstrap problem. But of course, we can try to use Gliozzi's method and play around with theta and see what we get. So that's something I think would be interesting to do in the near future. And we could just as well, I mean, since these blocks, D is a parameter, we could do just the epsilon expansion using the blocks just as well. And okay, that's pretty much all I wanted to say. And now I'll ask for questions, and if anyone else wants to intervene, I'll be happy. Thank you.
All right, thanks Antonio for this nice talk. So questions?
I'll ask a somewhat general question. For an ordinary boundary, there's a special operator related to the energy momentum tensor, which is connected with displacements along the boundary. Is there an analogous operator along the edge?
I did not check this, but presumably one would have the components of the stress tensor along the two directions that are orthogonal to the boundaries. And maybe there is sort of a displacement operator with the same components, say ZZ and YY, but presumably there could be a ZY type of operator, which might be associated to rotations of the system. I did not explore this, but I think that's a thing that should be studied, absolutely. Thanks for the observation.
No, but wait, this, I mean, having stress energy tensors on the edges, it could be quite non-trivial because first you take the bulk stress energy tensor and you go through boundary, and then you find like this pseudo stress energy tensor, you find displacement operator and so on. But then you need to go to the edge, and then the same thing will happen for all of these other components. So it might, I mean, it will probably be something like this, probably to rotation something, but it would be it's probably quite difficult to check it because there are like two limits you need to take, and there's one Bowie for each limit, and you have like all these components mixing around and so on.
Yeah, I agree. I mean, but presumably it would just be these components that are contained in the plane of the normals of the boundaries, I guess. And the expectation, of course, is that this cross component like ZY should be related to, I don't know. But you're right, it's obviously non-trivial and it should be worked out.
Okay, something I've been thinking about is that in this, in the bootstrap equation you write down, you only have exchanged boundary operators. Do you know if there's a correlator where you have exchanged edge operators as well?
Yes. Yes. So if you go to the two-point function in the bulk, the kinematics becomes pretty messy. You expect 3 cross ratios associated to 2 angles and a ratio of distances. And there you expect an infinite sum of edge operators. And the obvious way to see this is you take the bulk OPE of the two-point function, you get a sum of bulk operators, and then each bulk operator has a very non-trivial one-point function. No, sorry, maybe this is not the right channel to see it. What's the right channel to see it? Right, I presume the better channel to see it is to push the 2 operators to each boundary, to a separate boundary. And then you can now do the bulk boundary to edge OPE, and there will be an infinite sum over edge operators. Yeah, in this channel, this will be clear. Sorry, yeah. Let me repeat. So you take a two-point function of bulk operators, you push one operator to the boundary, and you have an infinite sum over boundary operators. Now you expand this into the edge, and there will be an infinite sum over edge operators, I presume. No, I think this is not correct. Sorry. Okay, you need to take the double OPE limit to see this. This is what I said before. You need to take the double boundary OPE limit. Okay. You push both operators to the boundary, and then you'll be left with an infinite sum over the edge. I'm sorry, this is the statement. This is a bit confusing just because there are 3 cross ratios, so it could not be achieved, as I was saying, with 1 OP. You need to take 2 OPs too. Yeah, sorry.
So there should be some limit where you take the angle to 0, but you make this distances very large, where this will look like a slab. So did you check that? Did you check that your analysis
basically
is what you're supposed to get there?
I don't think this theta going to 0 limit is very nice.
Well, you have to take theta to 0, but put all bulk operators very far away. So this limit will be just, it should look like this, like a slab. No?
That's true. I think you're right. But that's a tough limit, you see, because in a slab you have Casimir energies and you introduce a scale. So I didn't really check it. And even Cardi comments that this theta going to 0 limit is kind of problematic. And I think it's related to what I'm saying, that you are right that the geometry really becomes a slab, but then CFTs on a slab are not such an easy thing to look at. I guess you could also ask, what about if I send theta to pi?
I think it should be easier than what you're doing.
Are you thinking that when I just bring theta to 0, I effectively get a d-1 dimensional BCFT? Or are you thinking about something else?
I mean, in this limit, you'll just get two boundaries face to face. So the 1-point function of a bulk operator will still be trivial. It will have two non-trivial BOEs with each boundary. And you could also bootstrap that.
But I'm confused because, I'm confused because the way you're framing it, it seems that you're introducing a scale, right? It seems that there is like a distance between the boundaries, which is like dimensionful.
Sure.
Like in this parallel limit. And
indeed.
Here I don't think we can do much, right?
There will be a distance, indeed, that's true.
And this distance will, this is like a Casimir energy, and then you go back to this discussion of Marco Maineri, where we don't really know how to do, and you just have two boundaries parallel.
No, but that's not, that's not that problem. I mean, this is a perfectly well-defined problem. You just have two boundaries with two conformal invariant boundary conditions, and you can place an operator
and one bulk operator in the
deal.
middle. I agree, but this is a harder problem.
I think it's easier, but okay.
Maybe you're right.
More questions?
The other
Let me make a comment about what you're... Oh, sorry, Hugh, go ahead.
Oh, no, I was going to say the other special case, if you take theta equals pi over 2, and then the Green's functions by the methods of images would be relatively simple. Might be easier.
That's true. There is a nice simplification in that case, indeed, when theta goes to pi over 2. In my paper, I actually work in pi over 2 to make the calculations a bit simpler, and indeed.
In terms of doing bootstrap calculations, it might be more straightforward.
That's right. That's absolutely right. I also want to add that it seems very natural to take the theta going to pi limit to recover BCFT, but it's actually not so good to do that limit because of the boundary operator expansions that I'm doing. So since I have actually a picture here in the extra slides. So you might want to take the theta going to pi limit of the boundaries, but then the way we are doing this, the region of mutual convergence of the boundary OPEs would go to 0. It's clear to see why, because the boundary OPE on a given boundary can only converge up to here. This is the maximal hemisphere that we can draw. And therefore the region of convergence of the OPE is this little wedge. And when you open up to the boundary case, this becomes degenerate because only this line has a mutual region of convergence. So this boundary, this bootstrap equation is cute, but it cannot really reproduce the boundary limit like this. For that, one would need to use some type of bulk OPE to be able to reproduce theta going to pi, I presume.
For theta equals pi over 2, what's the region of convergence?
It's the full wedge. It's just the full, yeah. And there the cross ratios just go from eta to 1 over eta. So crossing is very simple.
Okay, if there are no more questions, let's thank Antonio again. Well, thank you very much. And
thank you, everyone.
And we reconvene at 2 p.m. for my talk.
Okay. See you then.